Hello everyone, and welcome back to our continuing introduction to Kotlin syntax. And today we're looking at part 2.2, which is essentially just looking at arrays and collections. So we're going to focus on arrays and collections just in this section, okay? Some of it we will have seen previously in different examples, but we will talk a bit more in depth into how we can access collections, create arrays, sets, lists, so on and so forth. Okay, so to talk about arrays and collections, here we have a little example of where we can use the array of function to create a particular array. Okay, so if you see down here, I'll just highlight it for you. Here we are creating a variable called myArray, using the array of function, passing in 4 separate numbers, and then we can convert that to it or print it out as a list. We can say println myArray.asAlist, so another function there, and then we can say print myArray and access it via an individual index too. So again, remember, indexes start from 0, same as Java. So the first println prints it out as a list. So again, we actually get those little square brackets, as you can see down here. And then likewise, when we print out a individual element or access an individual element, we say myArray2 is this one here, 0, 1, 2, and that's what we get printed out there, 6. Okay, so a simple example. So if you want to, if there's a need to convert kind of a set of elements, in this example numbers, into an array that you can process, we can use the array of function to do that. Now, some other examples, and this is really nice. You can create an array of mixed types, which is very different from Java. In Java, you'd have to go down the whole extend object route. You'd be casting, there'd be conversions going on. Whereas in Kotlin here, we can simply say something along the lines of this. Just highlight it there for you. Val myArray is assigned array of 4, 5, 6, 7, and then we have mixed types allowed, our strings. So that is a nice addition to the language. If we print it out, calling our asAlist function again, there we get 4, 5, 6, 7, and then mixed types allowed, which is really nice. Okay. To be a little bit more specific, if you want, to kind of help the compiler along as well for optimizing your code, we have individual kind of sub classes of that function, to describe it that way, where we can create individual integer arrays. So here we have, look, int array of, we can do it that way, right? Or kind of like in Java using generics and specifying a type, we can say array of and then pass in the type and then pass in the numbers. Likewise, there, the example, we have a char. We can do it for individual characters. We can do it for booleans. So boolean array of, right? But this is the little caveat. If you do go and declare and using, in this example, int array of or array of and then specifying the type int, you cannot then mix and match, because you've told the compiler this is going to be an array of integers or floats or doubles or strings, whatever you want. You cannot then mix and match. So just be kind of aware of that. Okay. If you want, as kind of placeholders, you can have an array of nulls. So in this example, we wanted to at some point hold integers. So we can say up here, we're saying val null array of nulls. So there's the function call, specifying then the type. There's our int and how many we want, 5. If we were to print that out, excuse me, if we were to print that out, we would get the following, because we're printing as a list again, so we get the square brackets, but we get 5 null elements. So then, but at a later stage, you could go ahead and you could assign integer values to those elements. Okay. In terms of just talking about the constructor, so the array constructor requires a size and a lambda function, and we'll talk about those lambda functions, lambda expressions, a lot more in the next few sections. But for the moment, if we just look at this example here, we're saying val int array, then we're calling the array function. Notice not the array of, this is the array function, so there's subtle differences. And then we're passing in a size, so there's our 6, And there's our lambda function. We've seen this before. We haven't really talked about it in any great detail. We will focus on it in a lot of detail in the next section. But there's our lambda function, our lambda expression inside the curly brackets. Okay, there's the kind of the parameter that we're passing in. There's the result, the expression body that we want returned. So in this example here, we would create individual 6 elements with the result of that expression. So whatever I happens to be, we would start. So I, in this case, we're saying I is initialized to 0, and we multiply by 2 every time. So then if we print out that list, this is what we get: 6 elements, 0, 2, 4, 6, 8, and 10. Okay, but like I say, we will come back to these lambda functions and lambda expressions later on. To talk a little bit more about collections now, unlike many languages, Kotlin distinguishes between mutable and immutable collections. So our lists, sets, maps, and all the rest of them. Precise control over exactly when collections can be edited is useful for eliminating bugs and for designing good APIs. So if we only want read-only access, we can actually use a particular collection to do that. Whereas if we want full control and kind of full CRUD features on a particular collection, we can choose a different one to do that. And again, we can have our code optimized accordingly. Okay, so just to talk a little bit about the mutable versus immutable. The Kotlin list out t, right, type is an interface that provides read-only operations. So you get a size function, a get function, a few others, but that's about it. Like in Java, it inherits from the collection class, right, and that in turn inherits from the iterable class. So if you can remember, if you would have done any work with collections in Java, we would have had these iterators that would have iterated, pardon the pun, over each element in the collection, and then that's like your pointer into the collection, and you use that to process your particular collection. Methods that change the list are added by the mutable list interface, and this pattern holds true for our sets and mutable sets, maps and mutable maps. Okay, so you just decide what you want your information you want held and how you want it looked up, for argument's sake, in the mutable map there. Okay, to look at some examples, so here's an example using mutable list. Okay, so if we see it here, just highlighted, we're saying val fruit mutable list of, and then so the type here is inferred, obviously, so it's banana, kiwi, fruit, mango, and apple, so we're just dealing with strings. If we can print it out, so we get there over here, we get our banana, kiwi, mango, and apple printed out. We can then go ahead and add an element, so very similar to identical to Java essentially, on our collection. So we can say .add pair, and again it's added at the end of our list. We print it out. We can change an individual element, so we can access it via an index. So we can say fruit 01 is assigned orange. So here we are, look, there's our 01 index, so there's our 1 index getting updated to orange. Likewise, we can say remove at a particular index, so here we are saying 2, so that would remove the mango element from our list. When we print it out at the end, we're left with those 4 particular elements. Okay, so kind of fairly straightforward, very similar to what you would have done using lists in Java. In another example here, we have our standard kind of declaration like we saw in the previous. We can declare a mutable list, and again we're just using our mutable list of, passing in 3 numbers. So that kind of that's read and write access. Whereas if we create a simple list based on that numbers, we can say val, and we just call it read only view just for the purposes of demonstration here. We're going to display that or declare that as a list. Note it's not not mutable list, it's just our simple list is assigned numbers. We can then go ahead, and if we want, we can print out those numbers, and we get the 1, 2, 3. We can add to those numbers, so that would add the element 4 at the end of that list. We can print out then the read-only list, because if we've assigned a reference, so read-only view is kind of pointing to the numbers mutable list, right? But if we try and call clear to empty that list, we can't do it. That won't compile because the read-only view has been declared as a list, which again has read-only access. Okay. Another little more complicated example. Here we have a class person, similar to what we would have seen in the previous examples. We have our underscore first name and our underscore last name, both are type strings, giving them default values. We then have a private, and that's kind of the key here, a private variable we're declaring called underscore items, which is mutable. Okay, so we're storing three string values there, 1, 2, and 3. And we also then declare a public variable items, right? And we override the get function to access that particular list, and we assign to it our we say underscore items dot to list. So we convert our mutable list essentially to a list of items that will store it in items, right? But we're overriding. We have as I see it there highlighted, we're kind of have this custom function get. We're overriding that function get, which will essentially link underscore items with items for accessing purposes. Okay, so in this case here, items returns a snapshot of the collection at a particular point in time, and that's guaranteed not to change, as toList just duplicates the items. Okay, so even though if and when items changes, right, when this class is created, it's as I said, it's a snapshot of a particular point in time. Just be aware of that. If we then try and say down here in our program, we create a person class, we can print out person.items, so we can access publicly the list of items. But if we try to say, and this is why we have it commented out, if we try to say person.items.clear, that won't compile again because items is read only. So from a design perspective, if we did want to be able to have read-write access, we would have to go back and remove that private modifier and make underscore items public. Look, most of the time you probably would do that. This is just kind of to demonstrate a mutable versus immutable lists, okay? As I say, not very practical in the real world, shall we say. Another example, working with set and hash set, okay? So here we are declaring our mutable set. Again, mutable set of just values 1, 2, and 3. We can print it out, we can add to it, and then we can print it out again. So initially, this is what we get. We have our 1, 2, 3, and then when we've added the 4, we get 1, 2, 3, 4. Now, we can then create an immutable set, initially giving it the values 9, 8, and 7, which we then print out. So yeah, as expected, we get 9, 8, and 7, right? But if we tried to add to that, or clear it, or delete, remove from it, whatever, the compiler will pick that up and notify you and say, sorry, this is immutable, it's read only, you can't carry out those functions. An example here, our hash set, right? This ignores duplicate items. So if you notice here, we have we've tried to add A, B, C, and C to a hash set called strings, right? But when we try and print it out, it's our $strings.size, right? We get 3, and the contents is A, B, and C. Okay, so it won't try and add, or it won't add the second C because it already exists. Likewise, excuse me, we can say strings.add, do the same thing, so we get our A, B, C, and D added to the end. Okay. And then to look at this kind of similar examples working with map and hash map, very similar stuff. Very kind of like what we, again, similar to what we would have done in the Java world. We create our mutable map, giving it some properties. So notice here we're saying W to Waterford, C to Cork. So W is like the lookup, the value is then the second property. So that's our map. So we want to map the value W to the key, sorry, the map the value Waterford to the key W. We can print that out. So that's what we get down here. W is Waterford, C is Cork. We can then add or put, as the function is with particular maps, another element. So we're going to say Dublin, give it a key of D, print that out. So there we get our Waterford, Cork and Dublin. And we can then update based on the key a particular field. So we can say our mutable map W. Notice that we're not using 0, 1, 2. We can actually use the lookup key. So that's quite useful. You could maybe have a phone number tied to a data, some unique identifiers, as opposed to the indexes. And we can say W is assigned Waterford. So we didn't update. If you notice there, we had a little spelling mistake on purpose. So now when we print it out again, we get our elements updated. The last bit there, last example, we're creating an immutable map. Again, specifying just this time we're identifying that the key is going to be an integer this time, and the value is going to be a string. Assign it there a map of, and here we are. This time it's an integer, 1 to 1, 2 to 2, and so on and so forth. You can do what you want. We can print it out, which is straightforward enough. We could retrieve individual elements, but if we try to update an individual element based on the index, or use our put, add to it, in this instance, that won't compile either, because again, it's read only, it's immutable. You can't change it. Once you've given it its values, you can't go and change it. Okay, so then we would, in the printout, we would get that 1 is to the text 1 and number 2 is to the text 2. Okay. That kind of wraps up that little section. Some familiar references there, additional sources that you can have a look at if you need to, and the other references that I've taken from some of the other slides. Okay, so kind of that's again the official docs are the go-to place, to be honest, and that's, as I say, that's that. And we will look at now collections in a bit more detail, but more specifically lambdas and those lambda expressions, and kind of functional programming in general, and a quick overview in the final section. Okay, so thank you. Hello everyone, and welcome back to our Kotlin syntax introduction. This is actually the last part now, part 2.3. Where we'll be looking at some kind of lambdas, functional programming, and so on and so forth. So just to wrap up, or to look at what we've covered, and we'll cover in part 2. So we've looked at writing classes and our data classes, and we'll see those now in the case studies. We've had a look at collections with arrays and collections, and now today we're going to look at or revisit the in operator. We've seen that, but in the context of collections, and lambdas. Again, we've kind of touched on these over some of the material so far. We haven't really talked about them in any great detail, but that's what we will do today. And we'll finish off then with a small little section on arguments, default and named. Again, we've seen this before, but just to talk about it in a little bit more detail. Okay, so to talk about the in operator and using lambdas within the context of how they're used to interact with collections, right? Here's a simple example we've seen already. So again, just to kind of highlight it there. Okay, we've seen this kind of thing before. We have our list of items there, list of strings, 3 strings, apple, banana, and kiwi fruit, and we can very simply navigate through them all with a simple for loop there, for item in items, and then we can print it out, and there we get apple, banana, and kiwi fruit printed out. So again, pretty straightforward. We've seen this kind of stuff before. What we can also do is we can check if a collection contains a particular object. So here we have a set using our setOff function. So again, the same val items, just it's a set this time. We can then use our when block to check to see essentially if or when orange is in items, print that out. Otherwise, when apple is in items, print that out. So again, very quite neat bit of code there, checking every element in items against that orange or against that apple, and if it matches, then it'll invoke the particular method that we want, or function that we want. A kind of a humorous graphic here, kind of a parody on the evolution graphic that we'd see in different contexts. Here we have our, right back at the start there, our machine language. right? Again, essentially all the ones and zeros. Then it progressed onto our assembly language, your div, sum, add, that kind of stuff. Procedural language, so kind of modula 2, bit of C on there as well. Then into our object oriented, our OO world, which we kind of still live in quite a lot. And Java will be a big one there. And where we're at the moment is our functional programming. And Kotlin is full of functional programming, functional expressions, and we have seen some of those already. We may not have discussed them in any great detail, but we will now over the next couple of slides, okay? And you'll be using this quite a lot going forward also. So a quick overview of functional programming. So in a nutshell, it's a style of programming where you focus on transforming data through the use of small expressions that ideally don't contain side effects. So in other words, if and when you call a function, in this example, kind of myFun a comma b, it will always return the same result. How that can be achieved is through using immutable data, right? And that is typical of a functional language. With this functional approach, we are expressing what we want done, not how to do it, okay? Some of the main characteristics of functional programming languages would be the following. They're designed on the concept of mathematical functions that use conditional expressions and recursion to perform computation. Now again, recursion can get quite confusing, but they've kind of leveraged it here in functional programming, and it's kind of under the hood in Kotlin, so we don't really have to worry about it too much. Supports higher order functions and lazy evaluation features. We will see this kind of lazy init stuff a bit in the Android side of things. And in terms of higher order functions, basically a function is referred to as a higher order function if it can accept at least one function as a parameter and return a function as a result. It doesn't have to, but if it can, it's a higher order function. Up to now, we've been using what's known as first order functions, which are they generally take parameters, calculate something, return a value if needs be, okay? And we will be looking at, again, a lot of examples now in a minute. Another characteristic, doesn't support flow controls like loop statements and conditional statements like our if-else and our switches or whens, right? They directly use the functions and functional calls. But like OOP, functional programming languages support popular concepts such as abstraction, encapsulation, inheritance, and polymorphism. So again, a lot of the stuff that you would be familiar with from Java still applies in the functional world. And again, the later versions of Java now do actually use lambdas and is moving towards that, trying to bring in some functional programming into it. A little bit more about lambdas. So lambdas aren't unique to Kotlin and have been around for many years in many other languages. Again, very similar to Java. Lambda expressions, sometimes we refer to them as lambda functions. So you may have come across other resources online or whatever. So they kind of mix and match. Sometimes the article might say lambda expressions, others might say lambda functions. We're talking about the same thing here, right? But they are essentially blocks of code. So they're anonymous functions, like you would have been familiar with in Java, right? That can be assigned to variables. So think about that for a second. You can actually store a block of code inside a variable, right? They can be passed as arguments to methods, right? Or they can actually be returned from a function call. And that's all applicable in languages that support these higher order functions. And again, Kotlin is one of those, okay? To look at it, to define a lambda expression, so to continue on our little discussion on lambdas, we can say something like the following. Okay, so up here, this is our kind of generic description or declaration of a lambda. So we can say val, give it a lambda name, give it a type, is assigned, and there's our expression, the argument list, and then our code body. So the point to note here, the only part of a lambda which isn't optional is the code body. So we only need this bit here, really. That's mandatory, or that's required, should I say. All the rest, so even declaring it as a variable, deciding on its type, passing in an argument list is all optional. Okay, and we will look at different examples now in due course. The argument, as I say, the argument list can be skipped or left out when defining at most one argument, and the type can often be inferred. So if you're only passing in one parameter into our lambda expression, you can actually leave it out. Now sometimes it's kind of worth leaving it in because it makes it a little bit easier to understand, but again, you don't have to. Likewise, you don't have to specify a type. So we've seen that type inference already in Kotlin. We don't always need the variable either. Lambdas can be passed directly as a function argument. So again, we could just take to show you here, we could actually just take all that, just that part there, the bit inside the curly brackets, and pass that as a parameter to a higher order function. Okay. And finally there, the type of the last command within a lambda block is the return type. So whatever it kind of evaluates the and whatever type that is, that's the return type. Okay. Just to look at some little examples. So here, a lambda expression is assigned to a variable greeting. The expression doesn't accept any parameters and doesn't return any value in this program. So if we look at it here, just very simple, we're saying val greeting, but there's our expression there, lambda expression inside the curly brackets, just one function call, println, prints hello, but it's assigned to our variable greeting, but we can invoke that like we would invoke a function. So we can say greeting and the braces or the brackets, and obviously when you're on it, you just get hello. Okay. Now, to look at a little slightly more complicated example, here we have a lambda expression that accepts two integers as parameters and returns the product of those two integers. So again, just to highlight those, here is our full lambda expression. Here we're specifying our two parameters, a and b, both ints, so a comma b, and the code body, or what we want as the result, is again the product, a times b. We can then call that as a function, assign it to a result, and print out that result. And then again, that's what we get printed to the screen. Okay, so a little bit more complicated, but showing us the power of those lambda expressions there. Getting it all done in kind of one line of code. Okay. To break that down a little bit, so in the previous example, the lambda expression was as follows. There's your argument list, there's your code body. Again, the lambda expression is enclosed inside those curly braces. So whenever we kind of see those curly braces, from when we've seen it previously and from now on, that's an actual lambda expression that we're passing in to a higher order function. Okay. Just to talk about lambdas in relation to collections. Okay, so lambdas are frequently used while working with collections. There are several built-in functions available, and we cover that now in the next few slides and give some examples of how we use them in the standard library that take lambdas to make our tasks easier. Okay, if the lambda expression accepts only one parameter or one argument, for argument's sake maybe a list of objects, right, you can refer to the argument by using the keyword it and it. So we've seen that already. Again, we didn't dwell on it too much, we didn't focus on it too much, but here now it becomes a kind of an integral part of using lambda expressions with collections. Okay, it is an implicit variable and can be omitted when it refers to a particular object in a single list argument, and that'll become a little bit more evident now when we look at the examples. Okay, so if you look at this one here, here we are using lambda expressions to filter and map collections. Okay, so we've seen this before. We've seen that the declaration, our fruits, there we are, just a list of 4 strings, banana, avocado, apple, kiwi. But what we can do is we can loop through that list using this higher order function. So that for each is a higher order function that belongs to the list interface. And notice no need for function brackets. Because it's a higher order function, we can leave those out altogether. So we just pass in the lambda expression. There we are using our it reference, right, which will reference the individual element that we're looping through in the collection. And then that's kind, as I said, that's like your parameter, so to speak. And here we are, what our code body, what we want executed, we want to just simply print out it, or print out the current element inside fruits as we navigate through it inside our higher order function for each. So what we get is down here, banana, avocado, apple and kiwi. But as we previously said, we can actually leave out, if we're only passing in one argument, we can actually leave that out. Okay, so if we look at the next example, here we are doing a little bit more, and this is quite useful as well. You can actually chain function calls. So here we are, here's our same list, but now we are filtering. We're saying dot filter, it dot starts with the letter capital A, and then we say dot for each printed out. So again, notice, because it's only the one parameter that we're using, the one reference, the it reference, we don't need to pass it in as an argument. We can just directly reference it. Okay, and what we get down here then is avocado and apple. Okay, and we can even go a step further. We can now chain another function, another higher order function called sorted by. So if you see it there, okay, so that will, surprise surprise, sort based on whatever the reference happens to be, and then we print it out. So we initially filter, we then sort it, and then print out every element. And you can see down the bottom there, then we get our apple AP and avocado AV. Okay, we can even convert it to a map and convert it to uppercase and then print it out. So here we're doing the same thing again, filtering, calling our sorted by, calling our dot map, and creating a map based on we're saying it dot to uppercase, and then printing them out. So again, if you look down here, here's what we get, our uppercase apple and avocado. So there's quite a lot of work going on there in a very short number of lines of code. It's very concise. Compare that to how you would do it, or how to try and do it in Java, and the lines of code would definitely be a lot more. Okay. Some other examples here, some sample functions, just to highlight them all there for you. See them all here. Okay, so we're creating a numbers variable, declaring a numbers variable, sorry, and in creating as a list, we simply just print out the whole list. So that's the first one we get up there. Okay, and then we just call some built-in functions on that particular collection. So we have our dot first, a dot last, a dot min, a dot fold right, which actually we can actually carry out some little block of code on it. So we're starting at 0, and it sums up all the elements, A and B, and then so as it goes from left to right, so fold right starts at 0, and we'll take each element and then add that A and B. So that will actually kind of cycle through each of the elements and add them up. We can just literally take the first two elements, or we can exclude the first two elements. Okay, so this is what we get over here. You can actually see the print statements based on those particular function calls. So it's quite a lot of functions that are part of those collection interfaces that can give you a lot of scope to do different things. Okay. Another few more sample functions here. Here we are, just showing again. We're declaring our numbers. There again, just a simple list. We print it out. That's what we get over here. We can then filter a list. So we're using using our filter higher order function, checking or filtering out on greater than. So there's our lambda expression, and filtering every element which is greater than or equal to 0. And then we print in that non-negative. So there's our 17, 13, and 12. So that's that one there. We can then use a for each on that numbers. Another expression. Again, this time we're just going to print out using our dollar sign there again. So kind of just getting it directly at the object itself. So we're evaluating whatever it references, and double it, so multiply by 2, and then that's what we get here. And finally, Again, you may be familiar with this from Java, the modulus operator. So we can filter based on just the even numbers. So again, the modulus gives you the remainder. So if the remainder happens to be 0, that means it's an even number. So we're saying dot filter and then dot for each, and we just print it out. But we're printing it out a little bit different than the others. We just put a little space there. So whereas the first two were kind of printed out as a default, kind of like a list, you get the square brackets. The next two we just printed out using it as an expression within a string. So it's just printed as text, and that's those two there. Okay, so again, just other examples of how we can work with lambda expressions and collections. Okay, virtually the same with the set. Just highlight there for you. So all the code is exactly the same. If you just want to work with a set instead, so you can see how these interfaces can be interchangeable. Another example here, just working with maps. We have our output over here. So there's the full output. Okay, so you can see here we're creating a map of counties, passing in little pair objects. It's just another way to create these if you want to store them as pairs, hence the pair element there. And again, we're just using our key. So our key here is, we're saying it's a string W. We're going to look up Waterford, similar with Cork's, C for Cork, D for Dublin there. We can run through each element. So we're saying our counties dot for each, print it out, and then print a comma and a space. Just one point to note there, just want to show you this. Notice there we're actually carrying out two individual statements, right? Two function calls, but they're all on the same line. If you want to call inside an expression, lambda expression, you need to delimitate or split them up with a semicolon. We could have put print on the next line, and that would be fine, and we wouldn't have a semicolon. But if you're going to put it all on the one line, you need that little semicolon in the middle. Okay, and then, as I said, that prints it out, prints the comma and a space, and that's what we get up there. We can do the same. We can counties dot to sorted map. We can convert it and then do a for each, do exactly the same, but this time it's sorted. You can see it there. Cork and Dublin, Waterford. We can filter it. So if the length of the value of that element, so here we are there. So if the length of the value, so that's essentially the text, if that's greater than or equal to 6, we'll print that out. Less than or equal to 6, print that out again, same as before. So there we're only getting Cork and Dublin. So Waterford gets excluded. And finally there, we can call another function there, filter values, where we can compare two. So we can filter, sort it, and between 5 and 9 characters. Okay, so again, a lot of functions there that you can kind of use to manipulate the data inside particular collections. But again, all done through lambda expressions there and there. Okay, and so our for each and our dot filter values, along with dot filter and for each, would all be higher order functions. Okay. So just to finish off this whole section, just to talk a little bit about arguments, both default and named arguments, just to talk a little bit about it. So our default arguments, they are optional. So in Java, you often have to duplicate code in order to define different variants of a method or a constructor. So for argument's sake, we say, if we refer back to our class person, where that person might have a last name, first name, maybe an address, maybe a phone number. If we wanted to allow the user to be able to create different versions of person, maybe some with an address, some without, we would have to have all these different constructors written to match the different parameters that the user would want to pass in. We thankfully Kotlin simplifies this by using default values for arguments. So it makes the arguments optional themselves. So once you define your class correctly with all the particular arguments you want, the rest is down to the user of the class. They can put in their own ones, they can accept the default ones. but it's all just the one constructor. We don't need to put in loads of different types like we would have had to do in Java. Okay, so just to look at some examples here. Here's our class nutrition facts. We can have, there's quite a lot there actually. There's 1, 2, 3, 4, 5, 6 say it for me, 6 arguments getting passed in. Okay, we have declared, they're all vals. We declared our types, so food name there is a string, calories is an int, but notice protein int is assigned 0, so we give default values: the protein, carbohydrates, fat, and description. So that means that they are optional parameters when we use this nutrition facts class and create an object of type nutrition facts. So if we look at the possible constructor calls down here, down the bottom, so if we look at this down here, okay, we could go and create one called val pizza, and we could say pass in pizza as the name, number of calories, and then we actually fill in 3 of the parameters are the proteins, the carbs, and the fat, and the description also. So that would be what we would kind of expected. That would be similar to Java, that we pass in all the parameters, right? But what we can also do is in pasta, we pass in the name, the carbohydrates, and the calories, and the protein, carbs, and fat. Notice there's no description been passed in, but that's okay. That pasta will have the default description, which we set to up here as the empty string. Okay, and we can even cut it down even further, because protein, carbs, fats, description are all optional parameters. A user of the class nutrition facts could just say val soup, and it's there, nutrition facts, soup, and calories, and that's it. So the default values would all then be 0, 0, 0 and the empty string. So it gives a lot of it's a lot neater code. It's a lot easier for then the user of the class when creating instances of that particular class. Okay. Just looking at some other examples there. We have our naming arguments makes your code more readable. So if you want to actually give it a different value, okay, so you don't want to stick to the default values. So the first one there, they were just passing them in like before, but you can, if you want, if we compare the first one there, right? Sorry, if we compare the first one past it's essentially 4 numbers. Not that intuitive in terms of what those numbers actually mean, but we can say something like this in the second one there: val burger, nutrition facts, hamburger. We can say calories is assigned that, fat is assigned that, protein is assigned that. So it does make our code, it's a little bit more work from the user's point of view, but it does make your code a lot more readable. Okay, and likewise there, the last one there, val rice, nutrition facts, we're passing in, giving a value for carbohydrates, giving a value for description. Okay, notice there's no protein value in there, so the protein would take the default value, which is set to 0. So a lot of flexibility in terms of how we can instantiate our particular objects through the one constructor, as opposed to having to have all these different types of constructors just to create an object. Okay. That concludes that part. Again, some of the similar references there. We have same references there taken from the original slides, going back to the official docs, and that's about it. So as I say, that wraps up the overall syntax side of things with Kotlin. There's one final thing to talk about in this set of slides, which is the code walkthrough. So we will return to that in the next bit. Okay, so thanks for that. Thanks for listening, and goodbye. Okay, welcome to our Placemark console version 3 kind of walkthrough. This version is getting a little bit more complicated. We're bringing in a lot of other features, so just to quickly look at those. So what we would have covered in part 1, We have all of those basic types, variables, functions, all the rest of it, same as the first two versions. But also we now have classes, data classes, and collections and arrays, and also interfaces. And we're looking at lambdas, and we're looking at arguments, both default and name. So there's a lot more in this version than there has been in the last two versions. Okay. So to look at the project structure, you can see here. I'll just give you a little bit better look at that. You can see that we have our controller packages. We have a main package, we have a models package, and we have a views package. So we've multiple packages. And we're trying to basically improve the design of this overall application. Okay. We're applying, as I said, the MVC pattern, model view controller pattern. I'll talk about that in a minute. And I'm trying to follow the same approach that my colleague Eamon will follow in the Android version of this, so that even that we say the naming conventions there for argument's sake. So if I just I'll just show you there now. So where we're using placemark mem store, placemark model, placemark store, placemark view for argument's sake, and placemark controller, you will see very similar classes in the Android version of this, especially with the placemark mem store model, placemark model, and placemark store interface. Okay, so I'll talk about those in a minute, but in the context of the project structure, you will see this again. So hopefully it'll be make it a bit easier to move across. Okay. So our main has been substantially reduced to one line of code, in fact. So what we use is essentially inside our main, where we had all the code and the functions and what have you, we now have a simple call to our placemark controller, and we call the start function, which kicks off the overall application. Okay, and we look at that now in a minute and see how that works. Okay. In terms of classes and interfaces, where they kind of crop up in our version 3 is in a lot of places, to be honest. So version 3 refactors the app to make use of the MVC, the model view controller design pattern. You may be aware of this, but just a little recap. It allows for separation of concerns, right? It allows us to, as I said, separate out different classes, different parts of the application, so that they do a specific job. And MVC is very relevant to Android development as well, and you will see this pattern and other patterns in the Android side of things also. So there's no harm in kind of getting a little bit of exposure to it now, so that when we start getting deeper into Android, you'll be familiar with the the concepts, and as I'm trying to do in this code, the class names as well and the interface names. Okay, so what we've done is a number of new classes and interfaces have been introduced to try and improve the overall design. Okay, so what we have here is our interface, placemark store, has at the moment 4 functions: a find all, find one, a create, and an update. And it takes our find all, if I just again highlight it there for you now. Our find all returns a list of placemark model objects. Find one, again, will return one individual one. Create takes a object of type placemark model, as does update. Okay, so these 4 functions are responsible for defining how our implementation classes will behave, and again that may change over time, but for the moment that's what we're going to have. So we're essentially declaring what functionality we want placemark store to represent. So when we go and implement that interface, we as the developers can decide how find all, how find one, how create, and how update are implemented. That, because of this approach, it's in Java as well. It's a lot of interface. You can use interfaces in Java also. It allows us to kind of define at the interface level, but then we implement at, sometimes I like to call it the concrete level, right? When we instantiate classes and implement that particular interface. So some of the rules that govern the usage of interfaces is the one here I have. Classes that implement this interface must implement these functions. So when we go ahead and we have a class that implements this interface, you as a developer have to implement those 4 functions. Even if it's just empty, you still have to put it in there. Otherwise, that class remains abstract and potentially another interface as well. So there's again a couple of rules governing this. So in our if we move on to the next slide there. Oh, sorry, hang on. Are we classes and interfaces? So just go down again. Okay, so we're moving on to the next slide. Okay, we have our class placemark store, right? But it's implementing our placemark mem store is implementing our placemark store interface. So here we see our functions, and again notice the override keyword. Okay, so that signifies that this is the implementation. For example, this one is the implementation of the method, function defined in our interface placemark store. Okay, so placemark mem store is like the concrete version of that particular interface. Okay, but if we define at the interface level, and we'll see this in examples later on, we can swap in and swap out different implementations. So in the last version, we'll actually have a placemark JSON store and actually store our placemarks to file. And Eamon will do the same with you. So we have a bit of overlap there, kind of intentionally, so that makes the transition a little bit easier. But just to give you a few notes on it there, this class implements placemark store. So note the modifier. We also have an internal function, which is we can see it there. Just calling it log all. It's just local to that particular class. Just want to draw your attention to this first of all. If you notice there now, we are creating a placemarks array list to hold our placemark model. So if you can remember, that's our data class that just has the ID, the title and description. So that's going to be managed and be accessible within our placemark mem store. So each of these find all, find one, create, update will interact with this particular placemarks variable. Okay. If we look and delve a little bit deeper into some of those functions, so perfect example here. Here's our onCreate, our create function. Takes the placemark that we want to add to our placemarks array list. So this is what we're passing in. So what we do inside it, we say our placemark, that placemark.id is assigned getID, and if you can remember, we have this getID helper function from the previous iteration of our application that just generates an ID. So that's going to update the placemark ID with a unique ID, and then we simply say placemarks.add placemark. Okay. Likewise with our update, you can see it there, passing in our placemark. We go off and we find or try and find, using our find one function, the placemark that we want based on its ID, placemark.id. Hopefully we find one. We stored and found placemark, but we do a little check to make sure. So if it's not null, so we have found something, we can say found placemark.title is assigned the title that's passed in, likewise the description. And again, this is a reference, so this will be updated inside the placemarks array list. Okay. We will see and kind of investigate those functions in more detail in the particular labs. I'm just trying to, as I said, focus on some of the most important ones here in our code walkthrough. Okay. So that's kind of just looking at the create and the update. In terms of our controller, okay, this is part of our MVC, our model view controller pattern. We have our class placemark controller, which if we look at the top here, does a couple of things. We are declaring a placemarks reference, which is an instance of our placemark memstore. Again, I'm following the same approach today and we'll be taking. We have a reference to a placemark view, which we'll talk about in a minute, and then we have our logger, and we've seen kind of this. We've seen this before. We have a number of methods. Okay, there's our start. We'll talk about that in a minute. That's our that's the start that was called in void main, which essentially starts the whole application. We have a menu. We have an add, a list, an update, a search, and a function just dummy data, which will, as I say, instantiate the our placemarks model. Okay, but the main purpose of this placemark controller class is to act as a link between the model and the view. If you notice, there's no interaction with the user, right? This controls the flow of data between the user and we'll call it storage for the moment. It's kind of been stored inside just a temporary array list. Ultimately, that can be stored in a JSON file. So again, the controller will manage that, but there's no prompting the user for data here inside the controller. That's one of the main principles behind the MVC pattern. That the M, which the model is just your data. The MV, the view is the interaction with the user, is the screen, is displaying menus, prompting for information, displaying information, and then the controller, so in our case placemark controller of MVC, sits in the middle and controls that flow of data between the model and the view. Okay, and that I suppose that's in a nutshell is what the MVC pattern tries to achieve. Okay, so if we follow those patterns, that we end up getting these kind of classes and that separation of concerns. Okay, so different functionality sitting inside different classes, and we just use those wherever we need to. Okay, so if we look at it here in a bit more detail, there's that start, right? That's what displays, it's the initial point of entry in our application. So and there it is there. You can see it here, function main, that's that start getting triggered, and it kicks off it triggers the CRUD features based on the user options from the view. Okay, so in our placemark view, that's where we will see all the menus and all the prompting for information, which in turn gets passed back to the controller, right? Inside that start via that menu call, and then goes off and triggers the add and update list and whatever needs to be back in the placemark memstore class. Okay, again, we'll see examples of that now in a minute. So looking at that add function inside our controller, if we look at what it does there, just to highlight there again. So here's our add. Okay, so it's quite concise. We declare a placemark model, so we can store that in it. Okay, we then, using our placemark view, we call a method add placemark data, which takes a placemark as a parameter. So we trigger the add placemark data, we pass in a placemark to that function, right? Depending on what that returns, we then go and say placemarks dot create a placemark. So we're passing in that same placemark, right, which hopefully will have been populated with our data, into our create function inside our placemarks reference. And our placemarks reference is our placemark memstore. So it's back in the memstore, it's actually stored in the array list. So again, this placemark controller is essentially just managing the flow of data from what the user enters and the individual title and description. That gets created, stored in a placemark model object, which gets passed into this placemark controller, which ultimately gets passed off to the placemark memstore and gets stored in the array list, and eventually will get stored in a JSON file. Okay, so that's, we're looking at interacting with both the model and the view to add a particular placemark. So here we are working with the view, here we are working with the model. Okay, and that's, again, you'll see a lot of that in the Android version as well. Okay. if we now look at the placemark view, which I sometimes refer to as the user facing or front facing class, right? We have inside it number of functions. There they are listed. Okay, so we have our menu, so that will display the menu to the user. We have a function called list placemarks, which again will list the placemarks. So if you can see the parameters, what we're passing in, look, we're passing in our placemarks reference, which is our placemark memstore, which internally will hold that list plus all the other functionality. If we want to show an individual placemark, we can do that through our show placemark function. We have, there's our add placemark data that we saw on the previous screen that was getting triggered. So again, just to show you there, look, there's the add placemark data, which look, returns a boolean. Okay, but just to go page up there for a second, just to show you again, there it is there. There's our placemark view instance calling. There's the add placemark data, which is inside the controller. And a couple of other ones there, update placemark data to trigger an update, and there's that get ID just to kind of generate that unique ID for a placemark object itself. Again, this represents it's user-facing class to present the console UI for the application. So responsible for displaying the user menu, displaying the placemarks, getting the placemark data, etc. Again, it's a bit convoluted because we are working with a console app. It doesn't. We could just as easily stick with not having to apply this pattern, but we both felt it was worth doing this to introduce you to these classes, the class names, so that when you do see the code again and these classes again in the Android version, they will be familiar to you. Okay, and as I said, hopefully make things a little bit easier. Looking at another function there, just to expand it out for you. Here's our function add placemark, which is getting the user data. So again, just highlight it all there. So there's the first look at any kind of console or any kind of print statements. Okay, so here we are, we're prompting the user, we're saying enter a title. Just show you there, sorry again. Here we are, enter a title. There's the read length that we've seen before, so reading it in with our potential null value getting returned. Doing the same with description, storing it in that placemark that's been passed in. So that's kind of like passed by reference. So that will, when it's passed in here and value set here, that will be available back in the controller and then back in the model. So we return a boolean just to make sure that yes, things are okay, so we can check to make sure that the data was entered correctly, and the other functions kind of work along the same lines. But that's the I think it's the first one I guess you'd implement in the lab, just been able to add a place mark to the application. It's all done again through the MVC. Just to look at the next there. So if we look at where arrays and collections are used within the application, we've seen some of this previously. So here's our instantiating inside our placemark memstore an array list of placemark model objects. So this is where the data is actually stored. That's managed inside the placemark memstore object, and that is then interacted with through the controller. There's never any direct movement of data from our placemark memstore to our view to what the user gets to see. That's all done through the controller. Okay. So again, look, we can set it up there. Sorry, like I say, for an array list, we can manually add like so. And again, that's what you will see in that dummy data function. Just moving on there. We can also carry out CRUD operations using our placemark memstore functions. So as well as being able to do it manually, here we are again just looking at our create again. So this is getting triggered inside the controller, which is triggered from the view. So we're passing in our place mark. There we are setting our ID, and here we are adding it to our place marks array list, and we just have a simple log there, log all, just to display to the user. And as we saw already, similar kind of stuff with our update, going off using our find one to find it, checking a little bit of validation just to make sure that we have found it, and if we have, then we update with the title and with the description, and we know at this point that title and description will hold particular values. Okay. And finally, quick look at where we use lambdas, and we would have touched on this now in the previous syntax part 2.3 section. So lambdas in place mark. So here the collections find function is a higher order function. Again, we talked about that before, which means we can assign it as a parameter and pass anonymous functions to it and use those lambda expressions. So just to look at it here, here we have a function search, takes an ID, returns a place mark model, and we have it tagged with the question mark in case we don't find it, so null may be returned. We are declaring internally, we have our var found place mark of type place mark model. I suppose in theory we could actually leave that out, right, because the type would be inferred. And we have place marks.find. There's our lambda expression. Okay, so our find then is going to return a place mark model object if the ID of the object we're looking at matches the ID that has been passed in. And we would have seen that in the previous example, but previous version, should I say, but we really didn't kind of focus on it in any great detail. In our log, we're referencing the it or the IT keyword again. So inside the log, which is that local function, we say placemarks.forEach. There's our expression again, logger.info, and we just within the string expression there, using our $, output that particular element, and it will loop through in our for each. Okay. So that, as I said, wraps up that version 3. Same references as we've seen before. Thanks for listening, and good luck with the lab. Thank you. See you now. Bye bye.